Good afternoon, everybody, and welcome to Beginner's Mind, Expert's Mind, or how we think about read, write, and learn to code. My name is Dawid Zalewski, and I'm going to be your host today for the next hour. A couple of words before I begin. This presentation has a lot of graphs in it sometimes, so it's kind of not, there is some code, but there are lots of graphs. And the second thing is maybe a bit how this presentation came to being. I'm an educator, and I teach students. I teach students who never had any, basically, any programming experience even. And it's a nice process, right, to see how people grow, how they develop, and how they learn. And this year, the first students that I taught to program started a PhD program in the computer science, a graduate program. So it's kind of makes you wonder how it's even possible that people learn to program, that they become so good in programming, how they comprehend, how they write. And this is roughly how this presentation came to being. So I don't know how many of you are fortunate enough to remember the first ever computer program that you wrote. Anybody here still remembers this? Like, great, some of you. Anybody remembers a first program that made a real impact on something? Yeah. So I'm also one of those persons. I do remember both of them, and in fact, it was one program. So this story begins when I was around 12, 13 years old. I was spending the holidays, the summer holidays with my cousin, doing the things boys do at this age, so playing, goofing around, right, outside, most of the time outside. But there was another thing. My cousin had this wondrous machine, a Commodore 64. And this was my first true experience with a personal computer. Of course, I mean, we didn't really program this machine, right? We didn't know how to program it. We were doing what boys were doing with computers at this time. We were playing computer games like River Ride, a very popular game then on a Commodore 64. And, you know, adults already then were against it totally. They didn't like it, so especially my aunt hated it when we played computer games in the evening, more so in the day. Doesn't matter, we did it anyway. Now, when I said that we didn't program it, I lied a bit. We did try to program, but at these times, you couldn't really do it like you would do it nowadays. You couldn't just go online, check a YouTube video tutorial. Basically, the only source of the knowledge of how to program computers were manuals that came with the computer, and that was all. There was also another thing, computer magazines, like Commodore magazine. And these were truly marvelous at these times. This was like your blog, YouTube, and everything condensed and put on paper. So it came with lots of hardware reviews, software reviews, tips, tricks, and it also had descriptions of games. But there was another thing. At these times, there were listings of programs published in the magazines. And I mean, this is, for example, a listing for a game. This is actually the listing for the game. You had to type it in, all of it, without making any mistakes, and run it, and you would have a game. And that's how you actually learned to program if you didn't have any other resources then. It was really a transformative experience because, first of all, when you typed in such a beast of code, you made mistakes, like granted, and you didn't know where they were, so debugging was mostly checking your code, if you were lucky enough that the program ran at all. And then you got curious, so you started trying, to figure out what the thing was doing, changing something, experimenting, and kind of figuring out what certain instructions did, how you could write your own programs. And we were also doing it with my cousin. So sometimes, not always, we were mostly, of course, playing computer games. And one particular evening, we were actually programming, so really making a proper program on our own, not just copying. And it was what you would call nowadays a chatbot, a very limited chatbot, but a chatbot nevertheless. It was late in the evening, and my aunt was getting agitated, visibly, mostly because we're still not in bed. She didn't like it, so she shouted to us from the kitchen that we should go to bed and that we should stop playing computer games. To which we shouted back, "We are not playing computer games, we are programming." Now, she didn't believe it because, first of all, she didn't know even what programming was. So we told her to come and see herself, for herself. She came in, and we demonstrated our marvelous chatbot. It looked pretty much like this, right? So it prompted the user, what is your question? My aunt was mostly interested in us going to bed, so that's roughly the question she asked. When will you go to bed? So she already, you know, started the conversation with the computer, thinking about us. To which, unfortunately, the computer responded, mind your own business. More questions. Now, this didn't land good, I must say. We went to bed directly after this piece of show, and that's also why this program made a piece of impact. We couldn't play games for the next 3 days. So that was my first program, a pretty cool one, if you look at it. That's the whole listing, roughly, because of course I cannot reproduce it fully, but that's how it looked like. It was bad, right? If you look at it, it was bad even for a Commodore 64 BASIC program. It's written in BASIC, using this very limited syntax. Like, the bad things about this program are mostly I'm using like variables for each string with an answer, a separate variable, bad naming. Then there is this very ugly if some random number is equal to something, then print something, and so on and so on. And there is even a go-to statement at the end, which makes it like a double as bad. Nowadays, I wouldn't write such a program. Even given the limited syntax and the limited tools of Commodore 64 BASIC, I would write it more or less like this. You don't see a lot of differences, but they are there. First of all, I don't declare plenty of variables. I have an array with responses. I have a subroutine, which I didn't have before. This is really a subroutine. You can see it because there is a return at the end. And this subroutine uses a kind of a lambda expression, I would say. It's not really a lambda expression, it's a single line function. Something like this existed. But nevertheless, the program became a bit more modular. There are good naming conventions. I mean, it looks, yeah, it doesn't look good, but let's say it looks better. There is still the go-to, but you cannot get rid of it. That's Commodore 64, that was the only option to loop. So the central question of this talk, or actually the two central questions of this talk, is like, first of all, how do you even learn programming if you cannot program and you don't really have resources to learn it, right? How is it possible that we learn programming? And the second central question is, how do you grow as a programmer? So how is it possible that starting with these very tiny baby steps, like declaring variables, you all of a sudden, after a couple of years, are able to write very complex code using very complex languages, artificial languages at best? And those two questions I will try to answer. Hopefully, you will be able to learn also something from it, as I was able to learn something from it when preparing this talk. Oh my God, sorry. So when it comes to the skill of programming, like whether you are able to learn to program or not, there was this hypothesis, and this hypothesis was very dominant for lots of years. And the hypothesis said that basically there is a geek gene. So some people can program, some cannot. And those who can program will learn programming and will do it quite fast, the rest just cannot do it. And this hypothesis is not without any substance. The reason for it is that something similar functions in mathematics. We are all born with some predisposition to be better at math or a bit worse at math. It doesn't mean that if you are born with no talent for math, you won't become very good at it. It will just take a bit more work. And if you don't believe it, well, do a simple experiment. I'm going to show you dots, black dots and white dots, plenty of them, and you have to decide within 10 seconds which are more frequent, the black ones or the white ones. So here's the image. No counting. Who's for the black? Are the black more common? Who's for the white? Black are winning. You couldn't count it. And those of you who voted black voted correctly. There are 37 black dots and 33 white dots. So what you just used is the approximate number system, something we are all born with. We just have this ability to quickly estimate the size of some set. We don't know why we need it, but we have it. This is an inborn ability, and we know we are born with it because even 6-month-old infants already show this ability. And of course, they don't count dots. It's impossible, right? But what you do is you show them different images. One image that change with some shapes that change in color, or actually that change shapes, let's say. And on the other image, the number of shape changes. And if the infants are drawn to the image with changing number of shapes, then we say that they have a preference for numerical, things. You can measure it at 6 months old, and this correlates with your later abilities in math. Hugely correlates. And what correlates, your abilities at math at like 3 years old naturally correlate with your abilities later on. So for many years, people believed there is also some kind of a geek gene, right? So we are born with the ability to program and some other cannot. And this was especially popular among educators. This was the Kemal hypothesis. Everybody who ever taught a computer course knows that something we talk about, but don't really very loud, is that a lot of courses, especially introductory courses, show the Kemal distribution or the bimodal distribution in the grades, right? Which basically means, some people can code, some people cannot. That's it. And we filter out those that cannot code. That's what we do at universities. Unfortunately, this is not true, or actually, fortunately, this is absolutely not true. So this hypothesis has been actually demystified. It's not true. And if you do rigorous statistical testing of the grades in the intro computer science courses, you will notice that 85% of them show a normal, absolutely normal distribution, nothing else. Around 7%, mere 7%, truly show bimodal distributions. So what what educators before thought or hypothesized was really a confirmation bias of their own beliefs. They wanted to believe that there are people who cannot program, and that's it. Everybody can program, and there is no geek gene. It just sometimes takes a bit more to learn programming. So another question is, what actually determines how fast we learn programming, or why, in fact, we can learn programming? What makes us learn fast? What makes us, what makes it that it clicks faster for us than for some other people? And there were different hypotheses about it. Like, the one very popular is that it's all about the language, right? The language is the key, because to be honest, like, programs look like language. You can just read it, like, if person's age is between 12 and 18, then do something, right? There is a lot of research being done on it. This is what you will see when you read papers. There is indeed a huge correlation between how good we are at learning third languages and how fast we learn programming. This exists. This is known for a fact. If you dig deeper into the data, you will notice also that how fast we learn third natural languages basically explains almost 50% of our rate of learning programming languages, which is a lot. There are also other things, right? There is math, and notice that math almost doesn't play any role, and there is fluid reasoning. And we'll come back to the fluid reasoning in a moment, what it is. If you don't believe just, simple tests and simple psychological tests, you can do the brain scans, and they will tell you exactly the same. What you see is the programmer's brain under the functional magnetic resonance imaging, and the highlighted areas are the so-called Brodmann areas, and those that show up are actually active when you try to read a piece of program. So what do you see there? Well, lots of Brodmann areas that light up are responsible for things that are linked to language, right? Like silent word reading or semantic memory or categorization. But there are also others, specifically working memory. So whether you can remember things, basically, some things very quickly. And there is also lots of problem solving. You've already seen problem solving under a different name, under the name of fluid intelligence, of fluid reasoning. This is basically your problem solving. Now, this is about learning. Now, if you move to how well we program, because that's a different skill, all of a sudden language almost disappears, and there is only this fluid reasoning and nothing else. Like, there are other things, you know, but they're not that important. Almost 50% of how well you program depends on your fluid reasoning skills. And this is the current consensus among the scientists. There are quite a few recent articles about it, and all of them show basically the same. Again, digging into the brain, you will notice the yellow areas. They are active when you are coding, and if you look at it, you will see that they overlap partially with logic, with math and language areas, but what's much more important, they're all part of the so-called frontal-parietal network, which is a part of the central executive system of our brain. And this is the part of the brain that always gets active when you solve problems, or when you connect things together, or when you draw analogies. So all this abstract reasoning, higher level abstract reasoning, is there. So let's talk about terminology for a moment, because this is important to get done. The theory of human intelligence roughly says that there are two types of intelligence, the crystallized intelligence and the fluid intelligence. So the crystallized intelligence is something, you know, learned procedures. You learned how to add 1 + 1, so you can also add 2 + 2, because you just follow a procedure. On the other hand, the fluid intelligence is your ability to basically reason in an abstract way, to solve problems that you have never seen before, to draw analogies, right? You know how to ride a bicycle, so you kind of can figure out how to ride a motorbike. It's an analogy, not in thinking, in doing, but you know, that's what it's about. So at the end of the day, it looks like, if you look at all the data, that what programming really is a piece of language. Some language is still involved because we use languages to describe our programs. There's the working memory, which seems quite there and important, and there's the fluid intelligence. And I want to go through all of them one by one, starting with the language and working memory, and finally a bit about the fluid intelligence, because, you know, apparently it determines around 50% of our skills, so why not? Let's start with the language. As I said, for many years people have claimed that programming is nothing else than reading and writing. It's like reading and writing prose. And you can think, yes, it is like this, because language is language, right? On the other hand, it's totally not. Like, if you have a piece of a book or a piece of prose, what you will do, you will start at the first line and you will start reading it, and it will be a very linear read. You go top down. Does anybody read programs like this? Anybody here? No, not really, right? What we do is something like that. This is a recording of a human gaze while trying to comprehend a program. So we go first top down, and then the dance starts. We go up, we focus on some area, we go up, back, down, and then we didn't understand something there, so, you know, it takes time. That's how we read programs. So it's totally unlike prose reading. It's something absolutely different. Let's do an experiment. Let's try to read a program, because most of the experiments are actually in program comprehension, right, that scientists do. So let's do an experiment. I'm going to show you a piece of code, and you're going to tell me what this piece of code does. Nothing else. It's a very simple piece of code. Hopefully, you will guess it correctly. So that's the piece of code. It's a function, and my question is, what does this function do? Binary search. Yes. How did you know it?
Name of the function. I assume that the name is correct.
Great. You just discovered a beacon. Beacons are fragments of code that we focus on and that we draw meaning from. So we build basically our understanding of the program based on the beacons. Usually there are function names or class names or variable names, very often, but not necessarily. There can be also some familiar patterns that you recognize or fragments of codes that are very characteristic for the algorithm or for a function. Like in this case, there are other beacons. If you are familiar with the binary search, you will also notice this one, which is always there somewhere. You always have to calculate the mid-cut when you do the binary search, and maybe you know this boundary or comparisons. Those are all very common in binary search algorithms, so if you are familiar with them, you will notice them. If you're an experienced programmer, this is the first thing that you notice when you read a piece of code. Those are the beacons. Now, it goes so far that if I actually showed you this piece of code, which is not that big, right? There are only 2 variables there, and it's quite short. And if you read it for like 20 seconds or so, you will be able to remember most of the lines of code that are there. So if I show you later on some of the lines that belong to the previous function and some which aren't from this function, you will be able to identify very confidently which are coming from the binary search and which are not. And unsurprisingly, mostly you will remember the beacons. So you will remember those lines that are, that belongs to the binary search. You will be absolutely certain they were there. This is dependent on your experience. The more experienced you are, the more beacons you remember. And the less experienced you are, well, the more of this extra code you will remember. So this has been measured multiple times and observed. Experienced programmers focus on those familiar fragments of code that give them meaning to the code. Where do actually those beacons go to, right? When you analyze a piece of code, when do those lines go to? How are you able to recall them? Well, they go to the short-term memory, right? Which in the theory of human memory is the piece of memory that's where you can store information that's quite recent. How recent? Around 20 seconds. That's what the span of the short-term memory is. And another thing about it, it has quite a limited capacity. So not many items will fit in there. I'm sometimes going to use another term, the working memory, which is for our purpose almost the same as the short-term memory. It's basically the STM plus some processing on top of it. Some scientists see the difference, some don't. We don't really care. Let's step up the game. So that was the easy program. Now another one. Anybody knows what this one does? Not that easy, right? Yeah. It takes a bit of time. It doesn't have any obvious beacons. Specifically, the name of the function doesn't really stand out. It's a process. And if you're not familiar with this particular algorithm, it will take a couple of seconds, maybe a minute, maybe 2, depending on how experienced you are, to really understand what it's doing and how it's doing. If you're familiar with this algorithm, some things will stand out. Right? Comparison of a pattern and a hash, then another comparison and a callback, and this update of the hash, which is kind of important here, right? Obviously, you could have guessed it also because the parameter names are not scrambled. This is a text and a pattern, so you know it's looking for a pattern in a text most likely, but the details are not that certain anymore. So this is very difficult to analyze if you are not familiar. And I'm not joking, you really have to spend some time. Also, because there are many variables at play. There are like 5 names variables that you have to track around, and there is another, actually it's a value that you also need to track to understand this code. And this doesn't sit well with our memory, with our working memory, because our working memory doesn't have so much capacity. So we cannot really track all those variables when we analyze the code. For many years, people believed that the capacity of human short-term memory is around 7 items. Now we know it's more around 4, or to be honest, many people start to believe that it's rather 3. So we cannot hold more than 3 or 4 pieces of information in our short-term memory. That's usually not enough. So what strategies do we apply to understand this code? The first strategy is the so-called chunking. We analyze a piece of code, and we group it under one chunk. Like this one, if pattern is matching, and if the hash is matching, then there is a callback, right? We chunk it under the callback if match. Done. The other one is we lean on our long-term memory. And that's quite surprising. Like, what does the long-term memory has to do with with analyzing the code, where everything just happens, right? It's quite fresh, and you cannot store it in the long-term memory. It's absolutely impossible. So let's do another experiment. I'm gonna do an experiment in remembering. We are going to try. I don't know what's going on with the sound. We're going to try to remember 12 different words, or you are going to try to remember 12 different words. You have 30 seconds to remember them. The time goes now. Yes, that was 30 seconds, exactly. Anybody still remembers all 12 of them? Anybody at least 6? Confidently? Okay, a few hands, that's good. It's not the majority, sadly. Why not? Okay, why not? It's obvious. Your short-term memory doesn't have the capacity to remember all of them. Now, let's make it possible. Because it is possible to remember all 12 words. So let's first put them on the screen and then assign some numbers to them and order them. Do you see the pattern? Like there is unicorn, 2 for the couple, 3 for the tree cycle, and so on and so on. Would you be able to remember them now? Yes, you will. Yeah. You will, because we just made an association, a powerful association with your long-term memory. So with the things that you know about, all right, you stored them. You basically just have to remember, yeah, that there are numbers from 1 to 12, and that's all, right? And we unscrambled it. Unscrambling makes lots of difference. So putting an order. We do remember lines of code better if they come in the order than if they don't come in the order. The second thing that happened is really this making a huge association. So you only store in your short-term memory the number 12, and that's all. You don't need anything else. The rest comes from your LTM. There's another trick that we do when we analyze code that's too long to remember. And this is the trick that chess players also use. Anybody plays here chess? Anybody? Like, do you know what this one is? Do you remember this when you look at it? Will you be able to remember it? Now, me neither. No, absolutely not. But experienced chess players will directly be able to recall this setup. No questions whatsoever, because it's a familiar setup. It's a Sicilian defense, the Scheveningen variation, and on top of it, this is the Keres attack to the Scheveningen variation of the Sicilian defense, and you can see it because of the pawn g4. At least the chess players can see it. They remember it because they stored those patterns, and current research says that grandmasters store around 10-15,000 of different patterns in their heads, and they have them readily available. We as programmers also do it, but our patterns are a bit different. This is a pattern that we have, right? A very common pattern. You don't store all of it. You don't store like I and then I is less than something. Oh my God, right? You don't do it. No, this is a for I loop. That's all. This is known as a programming plan, or that's at least how the cognitive scientists call it. We call it patterns, but this is known as a plan. We store them in the long-term memory. The only thing that we need to kind of remember when analyzing the program is the upper boundary, nothing else, because this changes. And this is the so-called slot. And slots are mediated with the short-term memory. The rest is safely there for you to draw on in the LTM. Now, this is, of course, expertise dependent, right? The more proficient you become with your code, the more patterns you will store. I doubt that there are 15,000 patterns that we as programmers have to remember, but I would guess it goes into hundreds, maybe over 1,000, right? Easily over 1,000. And that's how we basically analyze big pieces of code when we need to analyze them. We use chunking, and we lean onto the long-term memory to remember complex patterns and to understand what's going on there. So this kind of code, when you read it and when you try to comprehend it very quickly without a piece of paper and a pen, what you will do is most likely apply patterns. Like the first pattern here, well, there's a haystack and the needle pattern, a very common one, and there is a callback function pattern, also a common one. Then a bit of chunking, lots of local variables, a hash, maybe. Then there is a for I loop, and with a weird upper boundary, actually, something to remember. And then there is an if statement with the hash and the text comparison, and finally we do callback if the if is true. And final, I mean, at the end of the program, there's the hash update, and it's really strange, actually. So without going into details, that's roughly how you will remember it. That's how you will be able also to reproduce this program if asked for it. And again, the more experienced you are, the better you will be able to recall it. Mostly because if you're an experienced programmer, you will also build a hierarchy. So you won't remember it in a linear fashion. You will build a whole hierarchy of how it goes. Like variables will have their own chunk, and there will be a for loop, and in the for loop, things will be happening. If you are a novice, nah, unfortunately not. This is how you will represent mentally this program. You will just try to remember it in a very linear fashion, very ineffective. Nevertheless, that's how we'll do it. Now, all those nice things about how you read programs with beacons, with chunking, with leaning onto your long-term memory totally break down once you meet a program that looks like this. And now we are all in the same boat. This program does nobody knows what. And you have to analyze it because it's a piece of code that's somewhere in the code base, and you have to understand it. Nobody commented it. And it just looks awful, right? I agree, it looks awful. It's a lot, definitely, and it does a lot. So what you will do is basically will apply the same strategy. Doesn't matter if you're a novice or an experienced programmer, you will go bottom up with this program, trying to understand what it's doing in every single line, slowly remembering it, and building structure bottom up. And this is the only way. And when doing it, what you will be doing, or actually applying, is something that's called lowering the abstraction. That's something that was discovered when studying how mathematics students try to understand very abstract concepts. They don't understand them when they are presented with them during the lectures. They try to make them very concrete. So they lower the abstraction level by level, finally understand it, and when they have concrete examples they understand, they build up from it back to the abstraction. And that's roughly how you will do it also, because that's also how we analyze very abstract programs that we don't understand whatsoever. And it will work. Most likely you will be able to tell what the program does at the end. So what have we talked about so far? That programming is like reading and writing prose, but not exactly, right? Totally not exactly. And especially things that play a role are the working memory, where you have to store what's going on. There are patterns that you have to remember, otherwise you won't be able to comprehend long programs and to write long programs. And there's this fluid intelligence we keep on coming back to, and we'll touch it again more and more. What does happen when you try to read programs, and what does help, is beacons. So the familiar pieces of code or fragments of code, chunking, plans, abstraction lowering, and in the worst case, bottom-up analysis. So let's come back to this program, because that's how we started a moment ago, right? I played a trick on you. I must say, I deliberately removed beacons from it, because with the beacons, you would be directly able to tell me what this program did. Let's do the beacons. Here they are. The name is a filter by. You filter a tuple and you filter it by a predicate. Now it's easier, right? You know what the program does without reading it. Much, much better. So in a way, I deliberately ruined the program for you not to be able to understand what it does, right? Let's focus on it a bit. Let's talk about how not to ruin your programs from your brain's point of view. It's important. It's important because we tend to ruin our programs in multiple ways. And we tend to ruin them for our colleagues who review the code, who use the code, but also for ourselves 1 week further, right? So down the road, we shouldn't be doing it. And to understand what it is about, we have to introduce one term from the cognitive sciences, the cognitive load theory. The cognitive load is basically a measure of how difficult some problem is for you to understand and to work through it. And there are different ways or different types of cognitive load. There's the intrinsic cognitive load, extraneous, and there is the germane cognitive load. Now, the intrinsic is basically the difficulty of problem at hand. It can be expressed when it comes to the programming in the number of variables that you have to track, in the length of the code, in how many loops and nested if conditions you have. Extraneous is all the load that comes from external sources, like the name, like the functions of the libraries that you are calling. You have to know what they're doing. I mean, and they are not really a part of the problem, but you still need to know them. Side effects, but also domain knowledge. If you are programming in some specific domain, like engineering, you need some domain knowledge. And there is the germane load, and this is basically not really interesting for us. It's mostly about internalizing, learning totally new concepts when you try to understand a program. I have a very fitting example for this one, where all three types of cognitive load fit on one slide, and I took it from the CPP reference. I know they fit on into this picture because I experienced all three of them types of load when I first saw this piece of code. This is the famous visitor with the overloaded. How many of you are, anybody knows it? Everybody see it? Yeah, many of you have seen it before. This is the state visit on the variant with the overloaded. And it illustrates beautifully all three different types of cognitive load. Like the intrinsic is basically your lambda expressions, you need to know what they do, and the variant itself. There is a variant with three different values in it, or actually a vector of variants, right, with three different values stored. You have to remember it, you have to understand what they're doing. The extraneous cognitive load is the understanding what the variant itself is, you need to know it, and the state visit. This is a library function, you need to understand it. And then comes the germane cognitive load, right? This beast, which when you first see it, doesn't look like it can do anything whatsoever. And certainly it cannot be used in code. It can, and it takes some time to understand what it's doing. Now, when you write programs, you hardly can influence the main cognitive load. You also almost have no control over the external cognitive load, because it's just there. You need to call the functions. What you can influence is the intrinsic cognitive load, and you should. So let's come back to the program that was looking for a pattern in a piece of text. This is how it looked like, right? And it's already bad because the name of it is bad. This is already basically putting some weight on your intrinsic cognitive load. But we can make it much, much worse. That's the same program. Its functionality hasn't changed whatsoever. But if you write code like this, you should be in the Employees Hall of Fame in your company, on the back, somewhere at the back. It's a bad piece of code because first and foremost, we are now having lots of variables that we need to track, the values of them, 9 instead of 5. It becomes an impossible task. Don't write code like this. Next to those variables, there are also some internal variables in the lambdas. So it makes a total of 15 variables just to understand what this code does. For absolutely no reason whatsoever. Don't do it. Write code that's easy to understand, that has as limited scope as possible, that looks like this, right? Only 5 variables. Much better. Right? Everybody agrees it's better, right? You shouldn't. Names. Naming is important, and you've heard it many, many times. Naming is important because this is the first cue as to what something represents. This is this beacon, right? And here, the names are chosen in such a way that they are impossible basically to remember and to track. You won't be able. Not only you won't be able to tell what the variable represents, it will make it extremely difficult for you to track it because it's just rubbish. Because scientists like torturing people, they did this kind of experiments with programmers when they did exactly what I just showed you. They basically tracked what's the cognitive load when you try to analyze a program that makes sense and a program that doesn't make sense because of the naming. And the results were astonishing. A normal program with normal names can be quickly analyzed. A program that uses horrible names increases the cognitive load by more than 4 times. And this can be objectively measured by the amount of oxygen that your brain consumes when trying to analyze a program. So that's horrible. Don't do it. We like code like this much, much better, right? We understand it. Or wasn't it like this? It wasn't like this, right? Before we had much longer names. Unsurprisingly, longer names are better. Longer names, depending on the circumstances, make you read and write code around 25% faster and maintain the code. And if you're an experienced programmer, you are much more likely to use long names. Novice programmers tend to use around 50% more single-word identifiers than experienced programmers. So if you're a novice, please look up what your older colleagues are doing. They use long names. They dare to use very long names. They don't care that it takes space on the screen. It's just more readable. So do it. And maybe even instead of doing it like I did, write very descriptive names, because this really makes it readable. Now you truly can understand what this code is doing without really spending time analyzing the variables and tracking the values. So do it like this, much, much better. Now, I played a practical joke on you here. It's not really a joke, but I don't know if you've noticed it, but I made a cardinal sin. I mixed 2 different naming conventions here. And everybody has their favorite, right? Depending on your setting, on the company and on your personal preference. So let's solve it once and forever. Which one is better when it comes to programming, to comprehension, to solving problems, to maintenance, to everything? Is it the camel case or is it the snake case? The answer will come. Prepare. Here it is. It doesn't matter. Absolutely doesn't matter. There also, I mean, it was truly studied a lot by people who get funding from government, most likely. And some conclusions were pointing towards camel case, which was a bit better when it came to novices who were specifically trained in reading camel case. But this effect disappears with experience, and in fact, if there is a small insignificant effect, maybe the snake case is a bit better. Just because how our brains work. Like, we are used to spaces between words. That's the only reason. So don't care about it. What you should care about is about, yeah?
Did the study control for the prevalence of the case styles in different languages?
No. Unfortunately not. It mostly takes novices. I know a study about Java and a study about C++. So what you should do instead is put comments in your code, right? Lots of comments everywhere you can, because those are also beacons. And especially if your code is using a known pattern, like an OOP pattern or whatever pattern, or a known algorithm, write it down. Like this one implements the Rabin-Karp algorithm, write it. If you do it, you will be helping yourself and your colleagues in the experiments when the name of a pattern was used. The task completion of program maintenance, so changing a program, decreased in some situations up to 50% when the pattern was explicitly named. And the patterns used in this study were like observer or visitor. So only this already helps people understand the code much faster. Another thing, and this is really the last thing, don't lie to people. And especially don't lie in your code and with your code. This is a kind of, not the best naming, but it's an acceptable naming. You will see the so-called semantic cues in it, like there is a rolling hash used in the Rabin-Karp algorithm. There's a hash, the string function. They are self-explanatory what they're doing. Those are the so-called beacons or linguistic cues. If you write code like this that self-documents because of the naming, you are good. But some people write code like this. And you would be surprised, but in the open source projects, depending on the project, around 5% of the names look like this. Those are the so-called linguistic anti-patterns. When the name says something different than the code does, like one name here says shift by and takes an argument, but it doesn't shift by this value. It does something else. This is a lie. The other one says get hash. It tells you it will give you a hash, but it gives you two things instead of one. It's lying about what it's doing. Experienced C++ programmers will notice that it's also not a const function, so it most likely mutates something, and it's called get. It's another lie. Last but not least, there is a function called is. Is usually returns a boolean, like true or false. This one returns size, so multiple values. Another lie. There are around 20 odd different linguistic anti-patterns that you should avoid. Like, most of them go around about things like promising to return one but return many, or the other way around, or promising to change something but not doing it, and so on and so on. Again, linguistic anti-patterns totally overload us cognitively. We directly, our cognitive load as measured by the oxygen uptake in the brain rises around 50% when the code is riddled with some linguistic anti-patterns. So, good programs, happy brain, right? Use familiar and expressive names that tell a story. Keep the scope small. Your STM will thank you for it. Have regular structure. because it aids recognition, it aids leaning onto the long-term memory. Actively seek to use patterns when you can and document them when you can. Familiar patterns. Keep the APA promises that you make. Don't name your things differently than what they do. And last but not least, use consistent naming style, doesn't matter which. Right? And this leaves us with one unanswered question. How do I grow as a programmer? How do I go from not knowing anything to knowing so much? And we've been hinting towards the fluid intelligence a couple of times, and this is actually what Kate also told today in her keynote when she mentioned solving puzzles. Solving puzzles is fluid intelligence. So you might think, well, I will be solving puzzles and I will become a great programmer, right? So many different puzzles to choose from. I will be the hero when I'm able to solve all of them. Sadly, no. This doesn't help whatsoever. What you are looking for when trying to learn programming by solving puzzles is the so-called far transfer of skills. So you try to transfer your skills from one domain into another domain. This doesn't exist. Put it simply, all the meta-analysis that have been done up till now show that the far transfer of skills when it comes to fluid intelligence specifically, but also attention and working memory, doesn't exist. You just cannot transplant it from one domain to another. So this doesn't help. Now, with one exception. It seems like there is some evidence that your spatial reasoning does indeed help, and training in spatial reasoning does indeed help also with programming, a little bit. And it's also highly associated or correlated with how well you program at the end. So, for example, when students were measured on their spatial skills between starting a 4-year study program and their achievement, academic achievement, has been correlated with the initial test, you will notice that at the end of the studies, the correlation is the whopping 0.6. It's a lot for correlations. So this correlates, and there is some weak evidence that the far transfer exists there. So what should you be doing instead? Sadly, you should be reading lots of code. Reading lots of code, analyzing lots of code, and nothing else. Like, for example, imagine you don't know what an optional is. This is the first time you've seen an optional, and you encounter a piece of code like the fizz bus here that's using a state optional. Well, you just have to study it. You have to understand what it's doing. You have to read up on it, and you most likely will need to follow this model of lowering the abstraction when you go from a very high level to really understanding deeply what the state optional, for example, with the fizz bus makes, and then going back and constructing your mental model of what the state optional is. And this is not a happy story. Learning is hard, right? Specifically when you follow on with this code and see a piece like this that's totally abstract and makes a chain of responsibility using lambdas and optionals, and then you will be following what's called actually semantic waves. And this is this never-ending cycle of lowering abstraction, building a bit of understanding, going up, then hitting another roadblock, going down, up and down. This repeats on and on and on until you understand it. This is a hard way, and this is the only way that exists. So if you are looking for some shortcuts, they don't exist. Like, don't use ChatGPT. It won't help you. Don't use Google when you have a problem and you don't understand something. Try to figure it out yourself on your own before you even, go into your browser. There is an evidence that when you Google first, and it's a strong evidence, your retention of information will be around, let's say, not 20% worse. Yeah, it will be 20% worse, roughly, as compared to when you try to solve a problem without Googling first. And now you might ask me, is it the good way? I mean, is it not enough just if I study? I mean, if I program a lot? I mean, I will do my years of experience, I will become better. Doesn't matter what I do, right? No, not true. Years of experience correlates very weakly with your programming skills. What does correlate is what you do with those years of experience. Specifically, if you are learning, you will be a better programmer. If you are doing testing, writing tests, you will become a better programmer. And if you are doing code reviews, you will become a better programmer. Notice that the two last, or the two top here, mean reading code, changing code, understanding code, fixing bugs. This is what the last two are about mostly. So this makes you a better programmer. Now another question is, does it make sense? Won't I stop learning? Again, there was a keynote today about an aging programmer. No, you won't stop learning. Doesn't matter what age you are. There was a study in 2013 based on the Stack Overflow data when they measured two things. First of all, their reputation on the Stack Overflow for different age groups, and this grows, but that's normal, right? The longer you are on the Stack Overflow, the higher reputation will be, so of course the age is correlated. But they also measured the number of tags people used per age group. And surprisingly, it seems like the older you get, the more tags you are using. So your knowledge becomes broader and broader and broader, and this only plateaus when you're around 60. So when people start to think about retirement, spend more times, you know, with the grandchildren, maybe they are just not so active on Stack Overflow anymore because they have better things to do, right? But until 60, well, you never stop learning. So you will learn, and you will do it a lot. And one last thing, when you become this experienced programmer with tens of years of baggage after you, and you know pretty much everything, don't forget where you came from. And when you interview new programmers, for example, that apply for a position in your company, don't try to test them on the puzzles, intelligence, riddles, and so on. It doesn't make any sense. Doesn't predict your programming whatsoever. Instead, give them a piece of code, for example, and sit with them and try to fix a bug together with them, not just them. Also, don't be angry when they make small mistakes in this code, well, especially when they're novice. Don't be angry at your colleagues who just graduated and make really stupid mistakes, and that you have to fix those in your code review. That's normal. You see, when you see a piece of code like this, and when you're an experienced programmer, when you look at it for like a minute, you will be able to spot bugs or potential bugs very quickly. Some of them really stand out, like an overflow, potential overflow here, a comparison of an assigned and unsigned integer here, a kind of nasty business, and a certain overflow here. I'm overflowing absolutely, or going into the negative range in this case. Bad things. When you look at a program, you look at a program at different level of abstractions. And the high level of abstractions are usually quite difficult and come with experience. But the low level of abstraction, the logical and the physical, are very easy for everybody. The physical basically is a for is a keyword, nothing else. The logical is more about, well, this is a for I loop and it should work like this, nothing else. Now, it seems like, or it doesn't seem like, it is like this, that novice programmer tend many more mistakes, especially on the lower level of abstractions. So when it comes to basic things like syntax or grammatical errors, what we call grammatical errors, the reason for it is that more experienced you are, the more those tasks or comprehension of those low levels is automated. You just see it without thinking. So just to give you an example, this is fine code. It doesn't have any errors. This is a semantically implausible code, like doesn't make any sense, right? And this is a piece of code with a grammar violation. It's a grammar violation because we know that last index is an unsigned integer and I is a signed integer. It violates basically, yeah, the grammar of the language. Now, what you are seeing is the ECG records, so the brainwaves records of experts and novices when they are faced with a piece of code. And those are the normal responses when they see a proper piece of code with no errors whatsoever in it. When you introduce a semantic errors, the responses change. You'll see a big negative spike around 400 milliseconds. This is a spike that's associated also when you read a normal human language, like the language we now speak, and when you see a semantic error. Like if I said, for example, that a spider has 6 wheels, this is a semantic error, doesn't make sense. Now, a surprising difference is then when you have a grammar error, like a violation basically in the grammar of the language, you see a big dip in the experts and not such a big dip in the novices. This is because experts automate it. They just see it directly without thinking. Novices don't. They really have to spend their mental capacity to see the errors. So please do remember about it. This is the end. So to become a better programmer, read, write, code a lot. This is the only way. And learning to program well is a never-ending journey, right? You will end it when you stop program. Only then. And everybody was once a beginner. Please do remember about it. Everybody once wrote a program like this. Something to be proud of course. So please be kind and gentle, especially to your less experienced colleagues. They will thank you for it. Thank you. That's it. Oh yeah, I can take questions. They're not recorded, so.
No, now it is. I turned it on. That was a great talk. Thank you. Loved seeing all that. What came to mind when you were talking about like the long-term memory and short-term is, you know, a lot of times when developers are thinking about becoming managers, they're worried about if they're not coding every day that they're going to become quote unquote less technical or that kind of thing. And I've noticed that when I've taken maybe a few months off or something and I go back to coding, I still recognize all those beacons. I can still read the code and like quickly pick it up. And so I'm curious if you have any thoughts or if you've read any research about when somebody who's already very experienced takes time off but then goes back into it or that sort of thing, because I feel like it kind of relates to some of the memory things and whatnot, or even if you have any theories, just unfounded, that's fine too.
I'm not aware of any research about it, but that goes like with any knowledge that you have, right? It's the same story. If you don't refresh it from time to time, it will go. You don't have to program constantly, but you do need to refresh it from time to time. So put some intervals. Otherwise, after 5 years, yeah, you will forget it. Yeah.
I actually wrote this down partway through to ask about, do you have a nice list of anti-patterns that we can be watching for, thinking
yes.
about code reviews in the future?
So I should have mentioned it before, right? Because the slides will be also published, but you very often at the top of the slide, there was a direct reference to an article. And on all the slides that were drawing on some scientific knowledge, there is a reference, a title there of the publishing and the first author. And there is a list of anti-patterns, but I can also send it to you because I have it ready. So if you let me know, or I will just dump it into the Discord on the channel to the talk. So that's much easier. There is a list. Yeah. Oh no, I should stand here.
Thank you. Are there any effects from people with some degree of neurodivergence? For example, dyslexics frequently find learning spoken languages very difficult relative to people without dyslexia?
Yes, there is research on it. I'm not saying that I read all of it. I know there is a research about it. I'm not familiar with the details. As a nice tidbit of information, I can tell you that not always language is important when it comes to programming languages. Like when you're programming Scratch, whether you have any language abilities all of a sudden doesn't matter. So your language abilities or difficulties with processing language are only important if you also program with a computer language that resembles a language. Otherwise, those effects disappear. And I guess when time goes by, people will start also invest time into trying to come up with languages that lower the barrier for people who have problems with languages, with natural languages, let's say. But I haven't read any of those articles, so I cannot really comment on it. Okay. Yep.
In case you give this talk again, I think you had a bug on slide 66.
Thank you.
In the accumulate call, it wasn't using C in one of the cases, and in the other two it was.
Could be.
I'm not sure if it was a bug or not, but it stood out.
Thank you.
I think it was 66 and 65.
Now I got curious. You were fast. I mean, 66 was a lot of code, right? So,
It was somewhere around 66.
I think I know what you mean.
65.
So,
So in line 8, the accumulate function is not using C in the function. Whereas the other two are. Act time space.
thanks. That's the code comprehension. I mean, of somebody who's experienced, right? So, okay, one more question.
Just sort of curious. Should I? Hello? Test. Just sort of curious, do you think if you presented beginners with these sort of anti-patterns and said, hey, look out for all these things, that would ramp or accelerate their
No.
learning, or is that too much cognitive overload for them to
It's
start?
way too much. To understand what an anti-pattern is, you need to already be quite versed in programming.
Sure.
It's too early for it.
Thank you.
Okay. Thank you very much. Enjoy the break.